Hey friends, welcome. Today we will be discussing one of the topics of statistical thermodynamics, and that is Bose Einstein distribution law. Now in previous lecture we have seen the Maxwell-Boltzmann distribution law, wherein we have considered the particles, they are distinguishable. Now in case of Bose Einstein statistics, we are considering that the particles, they are indistinguishable, and we can occupy any number of particles in any particular energy level. So there is no restriction on occupation of the energy levels, that is, in particular energy level I could have one particle also, and in a particular energy level I could have all the particles also. Okay, and basically the particles having integral spin, that is in the whole number spin, which is whole number, like we have hydrogen, then we have deuterium, similarly we have nitrogen, we have helium. So those particles as well as photons, so these particles, they have integral spin, and hence these particles will follow Bose-Einstein distribution law, and the particles that are obeying Bose-Einstein's distribution law are known as bosons. Also the wave function of the bosons, they are symmetric with respect to the exchange of particles. And as we are talking about the wave function, this statistics, that is Bose-Einstein statistics, as well as there is one more statistics, that is Fermi-Dirac statistics. Both these statistics were given after the advancements of the quantum mechanics, and as a result these statistics are also referred as the quantum statistics. The particles are indistinguishable, so when we are exchanging the particles between the energy levels, then as the particles are indistinguishable, they will not give rise to any particular new microstate, and as a result the microstate will remain same. But if the particles were distinguishable, if we change the position, then that will give rise to new microstate. Over here, as the particles are indistinguishable, it will not give rise to new microstate. Now suppose if we are considering that we have ni number of particles, those ni number of particles are distributed amongst total ei amount of energy levels, and there are gi amount of various energy states, that is, this energy ei, it is further divided into the similar energies, or this is the statistical weight factor, or it is also known as the degeneracy, that is energy levels having similar energies, they are known as degenerate energy level, and gi is the statistical weight factor which gives us the degeneracy. Okay, so over here we need to distribute this ni number of particles between energy level ei with degeneracy gi. So over here, and also we know that there is no restriction on filling. So as there is no restriction on filling up of the energy levels, suppose if I have say 5 energy levels, and this 5 energy levels, if say I have 5 indistinguishable particles, so this 5 indistinguishable particles, I could arrange one particle in each energy level. Also I could arrange in such a manner that all the 5 particles in a single energy level. So if I am finding the particle where the particles are present, then when I am checking, say suppose I am checking from this side, this is empty, this is empty, this is empty, this is empty. So I have checked 4 partitions or 4 energy levels. So if the 4 energy levels are empty, then the particles are obviously present in the 5th energy levels, and hence we do not need to check all the gi energy levels, but when we are checking Gi minus 1 energy level, then we may find the particle, or we may find where the particles are present. So if the particles are not present in any of the four, then obviously, as the particles, or as there is no restriction, all the particles may be present in a single energy level also. Okay, so there are, so the total we need to check only Gi minus 1 amount of states, or the total states of the permutation will be Gi minus 1. So the total amount of permutation for Ni number of particles between this much amount, that is Gi minus 1 amount of particles, will be given as Ni plus Gi minus 1 and Gi minus 1 factorial. So this will give us the permutation of Ni amount of particles between Gi minus 1 amount of state, because if they are not present in Gi minus 1, then they will be present in the final. So we do not need to see that. Okay, also we know that the particles are indistinguishable. So this permutation, it also has the exchange of particles within themselves, also the exchange of energy levels within themselves. So we need to distribute, or we need to subtract those, or we need to remove those permutations also, and hence we can do Ni factorial into Gi minus 1 factorial. So this will remove the permutation of particles amongst themselves, also the permutation of energy levels amongst themselves, and hence the thermodynamic probability for such a distribution, it will be given as W is equal to Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1. So this will give us the permutation of the particles amongst different energy level, but this also consists of the permutation of particles within themselves, also the permutation of energy levels within themselves. So we need to remove the permutation of the particles within themselves as well as the permutation of the energy levels within themselves, and hence we are dividing the expression with Ni factorial as well as Gi minus 1 factorial, and this will give us the distribution, or this will give us the thermodynamic probability. So similarly for N0 we could write N0 G0, N0 G0, N1 G0, G1 and so on, and hence this we could represent it by capital Pi, which is multiplication of all the things. Okay, now further, in order to solve this, so again in this expression we will be obtaining the distribution or the expression which will give us the distribution of Ni number of particles between Ei amount of energy states. Okay, so we have our thermodynamic probability W, we have obtained it as capital Pi of Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. So this is our thermodynamic probability. Now we will be taking ln on both hand sides. So we will have ln of W is equal to, we know that pi is a multiplication function, and for ln it will be summation. So we will have summation of, we can take this over here, 1 is very small as compared to Ni and Gi, so we will be neglecting 1 over here. So we will have ln of Ni plus Gi factorial, this is in division, so we will have minus ln of Ni factorial minus ln of, again 1 is very less as compared to Gi, so 1 will be neglected, and minus of Gi factorial. Now we know that these are very large numbers, and we could apply Stirling's approximation to all the three terms, and Stirling's approximation we know it is, if we have say ln of x factorial, then that could be given as x ln x minus x, where x is a very large number, and as we are dealing with the gaseous system which is under equilibrium, these are also very large number. So our expression will become ln of W is equal to summation we will have Ni plus Gi into ln of Ni plus Gi minus Ni minus Gi. I am multiplying minus with both the terms directly, minus Ni ln Ni, and this minus will become plus, so plus Ni minus Gi ln Gi, and again this minus and this minus will become plus, and we will have plus Gi. So this Gi as well as this Ni will be cancelled out, and we will have ln of W is equal to summation Ni plus Gi into ln Ni plus Gi minus Ni ln Ni minus Gi ln Gi. Okay, now further we all know that when for most probable distribution, or first let us take the differentiation, or let us take first the differential of this expression. So when we differentiate it, we will have d ln of W, and we know that W is the thermodynamic probability, and for the most probable distribution, the value of thermodynamic probability is a unique value, and it is highest amongst all the other probability value, and hence the differential, that is for maxima, d ln W will be equal to 0. So the expression will also be equal to 0, and we will have d ln W. Now in different books this differentiation is solved in different manners, but I am showing it in the simplest manner. We will be differentiating these two terms, then this term, and then this term. So this we will be doing differentiation by parts. So we have summation, we will keep outside differentiation by parts, that is Ni plus Gi. We will be if we keep constant, then we will have differentiation of ln of x will be 1 upon x, and again it will be differentiated. Gi is constant, so this will be 0, and we will have Ni plus Gi constant. Differentiation of ln of Ni plus Gi will be Ni plus Gi, and into we will have dni plus, for the second part, ln of Ni plus Gi will be constant, and we will have differentiation of Ni, and differentiation of Gi will be 0. So we will have differentiation of Ni plus, again this will be differentiation by parts, so minus differentiation by parts. So we will have Ni, and differentiation of ln of n is 1 upon Ni into dni plus ln of Ni into dni, and the other terms, that is Gi terms, Gi are constant, and we know that the differentiation of constant will be 0, and hence all the terms representing Gi will be equal to 0, and this will be equal to 0. Now over here both these terms will be cancelled out, we are left with dni. Over here both these terms will be cancelled out, we are left with minus dni. So this plus dni minus dni will be cancelled out, we have minus sign over here as we have minus over here. So we have d ln W is equal to summation of, now we know that ln of minus will go into the division, so we will have ln of Ni plus Gi divided by Ni into dni, and that is equal to 0. So this will be summation of ln 1 plus Gi upon Ni into dni, and this is equal to 0. So this expression, it gives us the most probable gives us the most probable distribution. Now this most probable distribution we need to bind between the number of particles and between the total number of particles and the total energy of the system. So hence, as we have done in Maxwell-Boltzmann distribution, we know that the total number of particles, that is summation dni, is equal to 0, and also the differentiation of the energy, that is summation eni dni, is also equal to 0. So suppose this is our equation number 1, this is our equation number 2, and this is our equation number 3. So we will be applying, as the number of particles are constant, differentiation or summation of dni will be equal to 0. So we will be applying Lagrange's method, undetermined multipliers, and Lagrange's method. According to Lagrange's method, we will multiply this expression with alpha, we will multiply this expression with beta, and we will add equation number 2 and equation number 3, and we will subtract it from equation number 1, and as all the three are equal to 0, their operation will be equal to 0. Okay, so we will have summation alpha dni plus summation beta ei dni minus summation ln 1 plus gi by ni into dni, and that is equal to 0. Now I will separate dni terms on one hand side and summation terms on other hand side. So we will have summation of alpha plus beta ei minus ln 1 plus gi upon ni into dni, and that is equal to 0. Now over here we know it very well that individually dni is not equal to 0. Okay, because we know that the change, suppose we have same different energy levels, we have different energy levels, that is we have energy level E1, energy level E2, energy level E3, and so on. Okay, so over here suppose there are two particles, there are one particle, and there are three particles over here. So as we know that there is no restriction on the exchange, so we could exchange it. I will put one particle from E3 to E1 and one particle from E2 to one particle from E3 to E1. So the change in the particle, that is dn3, there are two particles are changed, so the change in the particle will be minus 2. dn2, the change in the particle will be plus 1, and the change in the particle for n1 will be again plus 1. Okay, so over here individual, when we look at dn1, dn2, dn3, they are not equal to 0, but when we sum it, then summation of dni, that is 1 plus 1 2 minus 2, and that is equal to 0. So the summation of dni will be equal to 0, but individual dn1, dn2, dn3 will not be equal to 0, and as dni is not equal to 0, all the terms which are present in the bracket should be equal to 0, and hence we could equate the terms in the bracket equal to 0, that is alpha plus beta ei minus ln of 1 plus gi upon ni, and that is equal to 0. When we rearrange it, we will have ln of 1 plus gi upon ni, that is equal to alpha plus beta ei. Now in order to remove the log, we will take anti-log, and we will have gi upon Ni, and this will be e raised to alpha into e raised to beta ei. We could further rearrange this expression, and this one we could take on right hand side, and we will rearrange this expression in the form of Ni, and hence we will have, we could take 1 on left that side, so gi upon Ni will be equal to e raised to alpha into e raised to beta ei minus 1, and when we inverse it, we will get Ni is equal to gi upon e raised to alpha into e raised to beta ei minus 1, and this is the final expression which represents the Bose Einstein distribution law, which gives the distribution of number of particles amongst different energy levels with certain amount of degeneracy. So hope the derivation is clear. Thank you very much.